I'm working through a bunch of electric field derivations. I've done electric field due to a rod, electric field due to a ring. We're going to use that. Today we're going to do the electric field due to a disk. And then we're going to use that to find the electric field due to parallel disks, which we call a capacitor. So there's a bunch of stuff to do. I'm going to do some Python. I'm going to do some Monte Carlo calculations. It's going to be great and long and epic, and I'm going to have a great time, and that's the most important thing. So let's just get to it. Review. If I have a single charge, Q, at location RQ, vector location RQ, and I want to find the electric field at a location RO, observation location, well, I need to find the vector from the charge to the location, and that's just going to be RO minus RQ. And then I can use this to find the vector value of the electric field. This R hat, super important, right? Because that gives this electric field as a vector. And then if I have more than one charge or an infinite number of charges, then I can just add up all the contributions to the electric field as vectors and get the result. I did that for like a line of charge. And I did that in the previous video, which I will link down below unless I forget, for a ring. For a ring of charge, if I want to find the electric field on the axis, so here's a side view. The nice thing about this is that a piece up here is going to make an electric field like that, a piece down here like that, and they have the same distance, so their XY components are going to cancel. You only are left with the Z direction, and this is our electric field due to a charge ring of radius R and a charge Q on the Z-axis, and that's the Z component of the electric field. And we're going to use that to find the electric field due to a disk. Okay, so I should have written this down already, but let me rewrite this just so I can have it on the next page. EZ 1 over 4 pi epsilon naught. Q, that's the total charge. Z, that's the distance along the Z-axis. R squared plus Z squared to the 3/2. So that's my electric field due to a ring. Now let's say that we have a disk instead of a ring. So let's draw a disk. It looks just like a ring, but it's not. There's my disk. And again, I'm going to be finding the electric field on the Z-axis. I don't really care to do that, draw that from the side, because I already know how that looks. I did it for the ring. And you could imagine, now, if I want to break this into point pieces, then I could have, how would you do that, right? How would I go, I could integrate in 2 dimensions. I have to do a 2-dimensional integral. So you could do that in Cartesian coordinates, and it would be kind of hard because your limits of integration are not constant, right? If I'm splitting these up this way, then I have to know the equation of the end of the circle to know the limits of integration, and it changes. So that's not easy. I could do it in polar coordinates, and my limits of integration would be easier, but then I have to have the area element in polar coordinates, and I just don't want to do that. So instead, I'm actually going to change colors here. Oh, I remember that was a bad marker. Here's green. I can break this not into point charges. I can break this into rings. So here's a ring of charge. So this disk is a sum of rings, right? So this ring has a radius of lowercase r, it's a variable, and a thickness of dr. And I know the electric field due to a ring on the z-axis. So let's just calculate the electric field due to this single ring on the z-axis, a location z away. And I'm going to call it dE. It's still z, so I'm just going to leave off the, okay, z. dE. Well, it's the same thing, 1 over 4 pi epsilon naught. Q, the charge of this ring, I'm going to call dQ. Z is a parameter on the z-axis. R is the radius of the ring, which is lowercase r. So now I just need to add up all these rings from r is 0 to r is capital R. That's it. And I could do that, but I do have one tiny problem, and that's this, right? So here, let's just review what's my integration, what changes as I change these rings? Well, this is a constant that doesn't change. Z doesn't change. That's a parameter that tells me how far from the disk I am. So the only thing that changes is that R, right? But then if I'm integrating over R, then I need my integration variable also over R. So let's get an expression for, just like we did with the rod, let's look at the total charge on this ring. I'm going to say this. I'm going to say dq over dA is equal to q over A. This says that the charge on this ring divided by the area of the ring is the total charge divided by the total area. And that is true if we have uniform charge density. So now we need to get dA. What's the area of this ring? Now, you may think this is a cheat, and it kind of is. But imagine I take that ring and I unroll it. And then so now it's a rectangle, has a length of dr. Well, a width. How long is it? Well, if I go all the way around, it would be 2 pi r. So dA is going to be 2 pi r dr. Right? It's the area of that thing. So now I can put all this together. dq over dA, which is 2 pi r dr, equals q over A. And A is just a constant. I'm going to leave it as A for right now. I guess not. A is pi r squared. So it's going to be q over pi r squared. So if I solve this for dq, I get dq equals q 2 pi r dr q over pi r squared. And just to check, right, because this should have units of charge, and so over here this should have units of charge too. Q has a unit of charge, and then have meters times meters over meter squared, so it does have units of charge. So there's my dq right there. So now I'm going to put this in up here, and then I can integrate. And that means get a new piece of paper. Okay, so let's just write down this dE equals, I'm going to write it all out, but I'm going to put it in my dq. Now let's just write it all out. 1 over 4 pi epsilon naught dq z over r squared plus z squared to the 3/2, and then dq is equal to 2 pi, I'll put it like this, q r dr over pi r squared. That's what I had. Okay. So now if I substitute this in, I get, and I'm going to pull all the constants out front as much as I can, but dEz 1 over 4 pi epsilon naught dq is going to be this. So let's just put in that whole thing right there. 2 pi q, I'm going to save the variables for later, over pi r squared, and then I have r dr, or there's a z. I'm going to put the z there too. Then I have r dr over r squared plus z squared to the 3/2. Okay, that cancels. We can go ahead and start canceling some other stuff, and it's going to look a little bit weird. We normally like to keep that 1 over 4 pi epsilon up, but no one ever does it that way, so that too will cancel with that. And then I get 1 over 2 pi r squared q z, and then I'm going to integrate both sides. So I'm integrating from r equals 0 to r equals r of this. R dr over r squared plus z squared to the 3/2. And that might look tough, but it's not tough, right? Because if you've done calculus practice before, you can remember, hey, look, if I call this u, then I have an r squared, and I take the derivative of u, I'm going to get an r dr. So let's say u equals r squared plus z squared. Then du is going to be equal to 2r dr. Z is a constant, so it goes away. So that means that this r dr is going to be 1/2 du, right? Because let's divide that both sides. So let's write this out. This integral of dEz is just e. So Ez is going to be all my constants, qz over 2 pi r squared. The integral, I'm going to leave that just blank. 1/2 du over u to the 3/2. And I can write that as qz over 2 pi r squared, the 1/2, so that becomes 4. I'll bring that out front. And then I'm going to write this as u to the negative 3/2. That's the way I like to think of it, du. Now I can use the power rule to integrate this, right? So with the power rule, we're going to integrate by adding 1 to this and then dividing by that value. So this is going to be equal to qz over 4 pi r squared. Add 1, it's going to be 1 plus negative 3/2 is negative 1/2. So I get u to the negative 1/2, and then I need to divide by that. So I get divide by 1/2 is going to be negative 2. And then I need to evaluate that from r equals 0 to r equals r. Let's go ahead and put back in our expression for u. So I get Ez equals negative, now that 2 is going to cancel, so I have negative qz over 2 pi r squared plus z squared, evaluated that r equals 0 and r equals r. So if I put in this, why am I getting a negative sign? I think it'll be okay. Yeah, it's going to be okay. So if I put in r equals r, I get negative qz over 2 pi r squared. Let's just factor that out. And then I put in r squared. Oh, it's to the negative 1/2. Negative 1/2. So it's going to be 1 over r squared plus z squared minus this 1 over z squared. Okay. To the 1/2. I'm messing up here. Okay, I think I got it. Yes, got it. Okay, this is correct. So now we just need to simplify this. So I'm going to just rewrite this. It's just algebra, people. It's not a big deal. Ez equals, that's a z, negative qz over 2 pi r squared times 1 over r squared plus z squared to the 1/2 minus 1 over z, right? Because I just have z squared. Okay, let's bring, I'm gonna bring negative z into the integral. Into the parentheses. So I get q over 2 pi r squared. Now if this is going to be negative, that's going to be positive, and I have z over z, which is just 1, minus z over the square root of r squared plus z squared to the 1/2. That's square root. And then I can do one other thing. Oh, there's an epsilon naught. Where did my epsilon naught go? Epsilon naught. Epsilon naught was right there. Dropped it. Okay, so there is an epsilon naught. So one of the things, Q is the total charge, R squared is the total area. So often we'll write this as Q over the area, which is the charge density, the surface area density, over 2 epsilon naught 1 minus z over r squared plus z squared to the 1/2. And that's the answer. That's the electric field in the z direction. Got that. Okay. Now, if z is less than r, right, so very close to the plate, then this right here, if z is much smaller, then I can just write this as z over r, right? Because this r squared plus z squared is just r squared, take the square root, and I get that. So I get e z is approximately equal to q over a over 2 epsilon naught 1 minus z over r. And then if z is super close, that's a 2. And so if z is much less than r, then z over r is approximately 0, and I get e is z is approximately q over a over 2 epsilon naught. Okay, we need to check, right? Check. Units. So do the units of this have the same units as electric field due to a point charge? It's 1 over epsilon naught. We got that. Charge on the top, q. And then it should be 1 over distance squared. So here I have area is distance squared. So this has the right units. This has units, no units. So this has to have no units. So I have meters over meter squared, square rooted. So that does, the units all work out. Which is the same as true over here. Same as true over here. So the units, check. Okay, what about as z goes to infinity? Well, as I get really far away, I can't use these formulas because those are approximations. But if I get really far away, the electric field should go to 0. If I put in as z gets really large, it's not quite clear here, right? But this, since I have a z squared, it becomes much greater than r squared. So this just becomes 1. I have 1 minus 1 is 0. So it does go to 0. Finally, what if r goes to 0? Then it should look like a point charge. And so if I have r is 0, I have, oh, it doesn't work. R is 0, I get z over z, 1. Wait, as z goes to infinity, this is, yeah. As r goes to 0, okay. I'm not sure about that. So that's check. That's a question mark. But I know that that's the right answer. So that's that. Now, what I want to do, since I have time, I have all the time in the world, I want to do a numerical calculation here using something that's fun, right? And this is going to be what's called a Monte Carlo calculation. Let's go back to our disk. So the problem with integrating over the surface area is that you have to do a two-dimensional integration, right? So that's why we broke it into rings to make things work better. And if you want to break this into finite point charges, it's still not easy to get them uniformly distributed because you have to come up with a rule for how to displace these. You can't use polar coordinates because then if you go an angle around here, then as you spread them out, they won't be uniformly spread. There's a trick to do that, but there's another trick, and that's called Monte Carlo. This is a technique used in physics that uses random numbers to distribute things. You can use it in a lot of different ways. We're going to use random numbers to distribute our charges. We're going to put a whole bunch of charges on the plate and then calculate the electric field due to all those charges. Now, in Web v Python, I'm going to write this down. In Web v Python, really the only random number function we have is this, random. And it gives a number between 0 and 1. So if this has a radius of r, what I'm going to do is generate dots in a square using 2 times random minus 1. This will give me a number between -1 to 1, right? Because 2 times random is 2 to 0. Subtract 1, now I have -1 to 1. And so I'm going to make points in a square, and then I'm going to eliminate them if they don't fit in a circle. And that way they will be uniformly distributed. And then I can calculate the electric field due to each piece. So there's a lot of work to do, but we're going to do this as simple as possible, and it's going to be a lot of fun. And then we can check and see if it agrees with our calculation right here. Okay, we can see if they agree. So here I am switching to Web v Python. I already got it pulled up. I want to make k 9 times 10 to the 9th. I'm also going to need epsilon naught, right? Because my other equation has epsilon naught. So let's say epsilon naught, I'm going to call it E0. It's just 1 divided by 4 times pi times 9 times 10 to the 9th. Okay, so that's useful. Now I need my charge, my total charge on the plate. I'm going to say it's 1 times 10 to the negative 8. I'm just picking some values here. The radius of the plate is 0.01, and that seems like it's still too small. That's better. And then my distance from the plate, my z-axis, I'm going to say z. I want it pretty close, 0.0001. Let's just pick a value. Okay, so I'm going to make a plate. I'm just going to make a plate. D1 equals a cylinder is an object in Web v Python. Its position is going to be at the origin. Its axis is for a cylinder, we have the position is one end and the axis is a vector to the other end. So let's just say axis is going to be in the z-axis, which is this way. So it's going to be vector 0, 0. I'm trying to think how thick I want it. Let's say z. Let's just do z for right now. It doesn't really matter, and that's gonna be too big. Yeah, and let's just run that. And there's my disk. Right, and I want to put points there. I'm just using that disk to see my points. So now let's make a bunch of points. So I like to do it this way: n equals 0. I'm gonna make 100. In lowercase n is my counter, capital N is the number of points I want to make. So what I'm going to do is to say while n is less than n equals n plus 1. So I'm going to count up to n. And then I'm going to create a random vector. RT is r times vector. Now I want it to be random in the x and the y direction, 0 in the z direction. So 2 times random minus 1, 2 times random minus 1, 0. And then I'm going to put a sphere there. And this is not going to be perfect, but it's going to be fine. Sphere, position equals that vector RT, radius equals, let's say R over 100, color equals color.yellow. And this should be in a square. Let's see if this works. Why is it so slow? Did I not do something right? There it goes. It didn't make any. Maybe you can't see them. That's probably you can't see them. Okay, let's make them bigger. You should be able to see those. Still can't. Oh, there they are. Wait. There's one. I did something wrong. Okay, let's see. R is that. 2 times random minus 1, 2 times random minus... Radius is R over 10. Let's print these values. I only have... Let's do 10. I'm not sure what I did wrong. They're tiny. Why are they so tiny? R times vector. 2 times random minus 1. 2 times random minus 1. 0. That's right. And R is 0.01. Oh, my cylinder, I didn't give it a radius up here. That's why. My cylinder is ginormous. Radius equals R. That's why. I had a 1 meter size thing. This will work. This will work. There it goes. Okay. So you'll notice here I only have 10. Let's do up to 100, make the sphere smaller, and they should be in a square. They're not perfect. So 100 points. I'm going to make this the radius of these, let's say 50. Okay. So there's my 100 points, and they're not in the disk, right? So I need to cut away the ones that aren't in a disk. I can do that by saying the following. I'm going to calculate the random number, And then I'll say if the magnitude of RT is less than R, then it should be in that circle. And then only in that case, I shouldn't have printed that, will I make the sphere. And only in that case will I add 1 to the value of n. Right there. So now that looks better. Okay. Now let's, we have all our charges. So I need to do up here, I need a dq, the charge of each one. It's going to be q divided by n. And I'm making all those charges. And I don't even actually want to display them. Because what if I want to do 1,000? That's not bad. But what if I want to do 10,000? Right? You can see that it's going to get kind of slow. That looks actually kind of cool. But I don't want to actually make spheres anymore. So instead, I'm going to do something a little bit different. I'm going to take those RT vectors and add them to a list. So I'll have a list of 10,000 things that I can use. And that's all I'm going to do first. So my list is going to be called RQS. It's an empty list. And then down here, I'm not going to make a sphere. Instead, I'm just going to add that RT to my list. So RQS equals RQS plus RT. So that's going to make my list of vectors. And that's only 1,000 right now. Now, what I want to do is to go through and find the vector electric field due to each one of those charges at my observation location. So let's make that RO observation location vector 0, 0, Z. Did I give a Z value? Yeah. And I can do this following trick. For RQ in RQS, this will go through the list, and each of those RQ vectors it's going to call RQ. And then I can use that RQ to calculate the electric field. So just like before, electric field is the vector 0, 0, 0. I need to add up to something, so I need to start with something. I'm going to calculate R. R is RO minus RQ. And then DE is K times DQ times norm R divided by mag R squared. And then I'm going to add that to the total. E equals E plus DE. And that should print it out. Now, let's print that. Newtons per coulomb. And I want a spacer. And I want to calculate the theoretical electric field. So let's do that. ET is going to be equal to, now I'm going to use that equation. Q over A, which I didn't calculate. A equals pi times R squared. So this is going to be equal to Q over A. Divided by 2 times epsilon naught times 1 minus Z divided by the square root of R squared plus Z squared. And let's print that. Print ET equals ET newtons per coulomb. And I feel like that was a lot to not have an error, but let's just run it because you never know. Maybe I did it right. Sometimes I do things right. Okay, so here's my electric field in the Z direction. I have 1.129 times 10 to the 6 and 1.78 times 10 to the 6. So not the same, but not terribly off. And every time I run this, I'm going to get a slightly different value because of the random numbers. And that's only with 1,000 points, right? That was only with 1,000 points. So here it's way off. Let's go up here and change this to 10,000 points. If I can do 1,000, I can do 10,000. And I'm not displaying them so it runs a little bit quicker. And here you see 1 times 10 to the 6, 1.7 times 10 to the 6. Let's just do 20, right? If I can do 10, I can do 20. Twice as many. And if it's not displaying the spheres, it runs a lot faster. And it's pretty close, right? And so as I add more and more numbers, I would get better and better and better values. And this does indeed work. But I'm showing you the proof of concept. I want to show you one more thing. I want to show you what happens when you have two parallel plates together. And then, because I said I would do that. So let's go back to the overhead and look at this. So let's use this expression for the electric field. And imagine that I have two plates. So I'm going to say EZ is Q over A over 2 epsilon naught 1 minus Z over R is the electric field due to one plate. But what if I have two plates? I'll draw them right here. So this is the Z direction. And let's say they're separated by a distance S. So this is plus Q, this is minus Q, and I want to find the electric field right here in the middle, or anywhere, a distance Z from that plate. Well, I'm going to get the electric field due to this plate. I'll call that E plus. And the electric field due to this plate is in the same direction, E minus, right? But they're not going to have the same value because as I get further from this plate, E plus is going to decrease, E minus is going to increase. So let's just find the expression for the total Z component. E Z is E plus Z plus E minus Z. And I've already taken into account the directions. So I have this Q over A over 2 epsilon naught times this one's going to be 1 minus Z over R. And this one is going to be plus 1. And then the distance from this is going to be equal to S minus Z, right? Because if I'm Z distance from that, I'm S minus Z from that. So instead of Z, I'm going to put minus S minus Z over R. And then if I just split this into two parts, I get equals Q over A over 2 epsilon naught. I have 1 plus 1 is 2. I have minus Z over R minus S over R plus Z over R. Cancel, cancel. And so this is going to be equal to Q over A over 2 epsilon naught 2 minus S over R, which is constant. And that's the most important thing about the electric field due to parallel plates, is that inside, if they're close, we can approximate them as having a constant magnitude electric field. And that's important for our calculations for a capacitor. Now, over here, if I use this formula, if you use even the closer formula, then it's obviously constant, and you just get QA over A over epsilon naught, because they'll both be in the same direction. But here, if I'm outside over here, they do not cancel, right? The electric field is not zero, because over here I have E plus, E minus is now that way, and E minus is going to be greater than E plus, so they're not going to cancel, and that's called the fringe field, and we'll talk about that later. Okay. So that's that. It was a lot of stuff, I admit, but we did some fun Python things. And it's a longer video, so if you made it to the end, you owe yourself a high five. Maybe go get yourself a coffee drink or something like that. But more physics to come. The end.